Every day, billions of digital connections are forged. It happens when your browser reaches out to an HTTPS website, or when a remote employee logs into the corporate server from their living room. To make these connections work, organizations rely on virtual private networks. A site-to-site VPN acts as a permanent, invisible cable linking two entire networks, like a branch office to headquarters. Meanwhile, a remote access VPN connects an individual user's device directly to that larger network. But both of these methods face the exact same problem. They have to route highly sensitive data through the completely open, chaotic infrastructure of the public internet. So, how exactly do networks guarantee that the files and passwords sent across this exposed digital highway stay hidden from unauthorized eyes and arrive exactly as intended? Maintaining security over the public web requires a layered architecture of trust protocols and invisible tunnels. The mandatory first step in building that system is establishing trust between a client device and a server through an SSL handshake. This animated diagram outlines how that trust begins. The client reaches out with a client hello. The server responds with a server hello and its digital certificate. Once verified, they exchange key parameters, agreeing on a shared session key, and secure communication begins. While SSL is designed to secure specific application-level sessions, like your web browser, it cannot easily transport raw internal network traffic or routing updates. To bridge two entire corporate sites, engineers deploy a protocol capable of carrying any data type, Generic Routing Encapsulation, or GRE. This visualization shows exactly how GRE operates. It takes private network traffic and wraps it entirely inside a standard public IP packet, giving it an address label so it can travel across the open web. There is one major flaw in this architecture. GRE provides the functional tunnel for routing, but it lacks any form of encryption. Anyone intercepting the traffic on the public internet can read the encapsulated data in plain text. To fix that glaring vulnerability, network engineers apply the IPsec protocol suite directly over the GRE tunnel to lock it down. IPsec uses a component called IKE, Internet Key Exchange, to negotiate the complex encryption keys and establish the strict parameters of that secure tunnel before any actual data flows. But before those secure keys can be negotiated, the devices face the same hurdle as our browser. They need to prove exactly who they are. In smaller networks, administrators often rely on pre-shared keys, or PSK. This functions as a simple shared password that both ends of the VPN tunnel type in to authenticate each other. However, a single shared password quickly becomes a management nightmare for a global enterprise. Large, secure environments require certificate-based authentication. Instead of relying on a shared secret, a trusted third party, known as a certificate authority, issues a unique digital certificate to every individual device, giving it a cryptographically verified identity. While a basic password might work to connect two small branch offices, scaling security across thousands of corporate users demands these unique cryptographic certificates paired with IPsec to actually secure the network tunnel. Building a fortified tunnel is the first step, but protecting the packets inside requires two specific simultaneous operations. This animated diagram illustrates the first process, data confidentiality. Running the readable packet payload through encryption algorithms like AES converts it into a completely scrambled format. The second layer adds beta integrity. Hashing algorithms generate a mathematical fingerprint, verifying the packet remains unaltered. Confidentiality ensures that an intercepted packet is useless to an unauthorized viewer, while integrity detects if a packet was modified in transit. A failure in either mechanism leaves the connection vulnerable to exploitation. Once this airtight system is running, routing absolutely everything through the VPN can cause traffic jams. To optimize network performance, engineers implement a technique called split tunneling. This branching graphic shows how split tunneling works in practice. Critical traffic, like internal office applications, is routed securely through the encrypted VPN. Meanwhile, high bandwidth traffic, like watching a YouTube video, is sent directly out to the open internet. But opening that secondary path creates a massive security blind spot. Any data sent straight to the internet completely bypasses the protections of the IPsec tunnel. Faster, more urgent tone. If a remote user accidentally accesses a malicious website on that unsecured path, the attacker can compromise the device itself, rendering the nearby VPN tunnel practically useless. Building a secure network demands precision at every layer. An SSL handshake initiates trust, GRE builds the routing path, IPsec locks the tunnel doors, and confidentiality alongside integrity ensure the data survives the journey.